Welcome back, everyone, and we're now moving into our first plenary session. So for this session, we're going to start by a sort of discussion from Helene about what we are meaning by a sustained mode in terms of this kind of CMIP community. And then we're going to move on to a wider user perspective, where we've got a few presentations from users and a user panel discussing the different needs. And that'll be led by Anka and Carlo from Copernicus Climate Change Services. So I'll start off by handing over to Helene Hewitt, who's the CMIP panel co-chair, to give the presentation on what we're meaning by a sustained mode.
Okay, thanks, Eleanor. Yeah, first of all, just on behalf of the CMIP panel, just to say thank you to everybody for all your efforts on the forcing task team and all other contributions to CMIP, which are enormous. Eleanor, are you going to share the slides? So basically what I was going to talk about is just, some thoughts that we've had on the panel and from wider discussions about what we mean by sustained mode or, operationalization, as some people might refer to it. So, why would we be discussing this? Well, many of you know this. So, many of the applications for CMIP have become, maybe quasi-operational. So there's a state estimate of current policy in the global stocktake every 5 years. There's now many climate service activities, including, of course, the Copernicus Climate Change Service, but others also in the States. And Destination Earth is obviously has ambitions to do something more operational, if you like. Alongside this, as many people are probably aware, there's been a number of papers from prominent researchers who are suggesting that we need to do something different to the current situation. So the paper by Christian Jakob and co-authors, where they're discussing, rather than CMIP perhaps has research mixed with providing products to service providers, splitting those out, so you have what's needed for climate services separate to what's needed from research. The paper by Bjorn Stevens, where I think the schematic is the balloons are letting go of the projections from CMIP, so letting CMIP just be research. The paper by Colin Jones and co-authors, talking about how we could better link up CMIP with Cordex, with the impacts assessment work in a perhaps slightly different vision of something more sustained for policy. And the recent paper by Veronica, who was the previous chair of the CMIP panel for CMIP7, basically outlining, what could be a way. What could be included in this and in a sustained mode, and I think that's really what many of us would see as being in that. So if we just go to, and I would also say, so it's not on there because it's not a paper, but Paco, who many of you may know, although there isn't a paper, I have seen him talk many times about how in CMIP every 5 to 7 years we're producing this Rolls-Royce type product. And perhaps we need to move to a more of a factory type production for some of the work. So at the recent meeting of ESMO, the System Modelling and Observations in WCRP, with the Working Group for Coupled Modelling, it was agreed to set up a scoping group within WCRP to look at this. So that's chaired by myself and Greg Flato, who's just for the moment, at least, I believe still the WGCM co-chair. It also includes people from the Working Group on Numerical Experimentation and others within ESMO. And we're supposed to be reporting back on the need for a long-term sustained CMIP mode. So this discussion is, of course, really relevant to this, who the stakeholders might be, the viable mechanisms, funding, timing of this. So the idea was to report back in a relatively short time frame, say the next 6 months or so, I would say is going slowly, but I think that's because the questions are really difficult. So it's not easy to write down the answers to things you don't always know where to exactly start. So just to say a bit more about that on the next slide. So, you know, and this is also agreeing with what Veronica had written. I think what we see would be under discussion for a sustained mode is both the forcings, as we're discussing now, but perhaps also the scenarios, some updates to simulations or new simulations. Obviously, things like the data request and benchmarking or metrics of the output. And it's, you know, what I think is really important, and I'm sorry, I meant to emphasize this on the last slide, is that we're not, the reason that we don't really use the term operational, and at least from the CMIP panel side, unlike some of the papers that have been published, is because it's not like a weather forecast. We're not trying to do things on that rapid turnover. And so sustained mode seems a much, it seems like the kind of term where we can take people with us from the broadest range of the community, whereas I think, you know, operational seems to be a divisive term. And so, you know, I think sustained is much better and suits climate better. Next slide. So perhaps, you know, and, you know, this fits a bit with what Seb's talked about, that perhaps on an annual basis, we might see an extension of the historical forcings. We might see we could potentially have new scenarios. The impact assessment modelling community are looking at, or the integrated assessment modelling community, sorry, have a new initiative called Compass, where they're trying to set up new scenarios every year. So that fits well. Perhaps some extension of historical simulations. Maybe you know, it seems unlikely that we need new full scenario MIP type experiments every year, but maybe every 5 years, perhaps, you know, aligned perhaps with the global stock take. We could have that sort of full suite, and perhaps also on that sort of timescale, something like an update of the historical forcings. But I also think it's really important to, when we're having this discussion about the sustained mode, as we've talked about, it's not separate from research. So we really need the research to be acknowledged, and that it can benefit from the infrastructure that this could provide in a more sustainable way, but also pull through the new science into this sustained mode. Obviously, as we've talked about, you know, there are difficulties with the extensions and updates of the forcing in the current status. So the research funding, where the next grant might be coming from, that people are either working as volunteers, or at least in the margins, perhaps, of their day job, or perhaps it's taken over their day job in many cases, I think. There's a lack of resilience, you know, many single points of failure, many, you know, perhaps limited options for backfilling. You know, this is a problem even in, you know, the Met Office, for example, but much harder in a university where you've got less people to draw on, perhaps. And you know, this balance between the effort directed towards updates rather than just extensions, when perhaps what some of the stakeholders want is the extensions rather than the full updates. So we believe there are stakeholders, and it would be good, and I hope we can do it, some of this will, at this meeting, will go towards this, to actually clarify exactly the range of these stakeholders. I'm sure that the Copernicus Climate Change Service are a stakeholder who are interested. The WMO Annual to Decadal Forecast, which is a whole group of providers, are interested in the forcings, at least, perhaps other aspects, detection and attribution. Within the WMO, there is data sharing available. They have this integrated post-processing system. If data were available there, perhaps that could extend the global reach of the climate services. But we really do need to think about what the viable funding mechanisms which really reflect the global diversity, as we've heard about just even this morning. And so the next slide. So is there a viable mechanism? So these are, we've really struggled to think about these, but I think it's lots of people have put forward papers about, oh, we should do this and we should do that, but nobody's actually said this is how we will do it, how we will govern it, how we will fund it. And so PACO, for example, has highlighted particularly the WMO lead centre style, which they do for the annual to decadal forecast. And I've just got a slide on that in a minute. Perhaps we could set up some dedicated type centres. That's perhaps more in the EVE style. Perhaps there's just funding which will support this, perhaps C3S, other funding outside of Europe. Just as we were talking earlier, I was involved particularly when we set up a consortium with a shared ocean model across Europe. And in that style, we had a consortium agreement, and people signed up to that by putting together a minimal amount of effort. And that consortium then has ways of working that are put together for the code, for example, and come together once a year to update the code. So maybe that might be another might fit as a governance type structure. We go to, and then just to say about the WMO type activity. So the annual to decadal climate prediction really started in many ways as a MIP of CMIP, and some of that still carries on as the DCPP. But it was set up as a operational activity, which is within the realms of WMO. The Met Office, as it happens, is the lead centre for this, but it brings together predictions from a whole load of other global producing centres. So DWD, BSC, the Canadian CSIRO, and they have, I believe, more of an obligation to provide them. And then there are contributing centres who have less obligation. So I don't know whether this would work for the forcings, but obviously we're grappling around to try and think what could work and how we could make this all hang together. So in summary, I think that, there are stakeholders for regular production of some of the CMIP outputs. I think a sustained mode gives us the best chance of taking everybody with us rather than talking too much about operationalisation. In spite of the increased calls, the governance and funding are really unclear, and we have spent time trying to think about this. Particular issues for the forcing, with the extensions versus updates, the funding, and many other things that we've talked about. And just to emphasise that we are not by any means with this wanting to abandon the research within CMIP, because that's really crucial for answering the new science questions and pulling through to any kind of regular production. And I think I also wrote this in the chat. I actually see that moving some things to a more sustained type mode will actually support more science. We see that with weather, we see that with the seasonal forecast. It makes it so easy for research to demonstrate impact. So I think people shouldn't feel kind of scared about it. I think, they can kind of coexist really well. So that's it.
Thank you very much, Helene. We've got time for maybe a couple of questions. So Anna online. Oh, sorry, you're clapping. I was getting my symbols confused. Has anyone got a question for Helene?
Yeah, hi, Robin Hogan from ECMWF. I don't know if this is the place to talk about a specific case, but it might help illuminate the kind of sustained mode you're talking about. So in the case of radiation in both our weather forecasts and our seasonal forecasts and our reanalysis, I kind of need 6 numbers, which are the concentrations of the big 3 greenhouse gases, the 2 CFCs, 11 and 12, and also the total solar irradiance. Something Gavin mentioned yesterday was that our ERA 5 is already using CMIP7 forcings, which are very out of date. And the reason is that it's an 8-year-old cycle now. And at that time, we didn't have CMIP6, and we fix on CMIP5 forcings, both for the past and the future. And that was kind of fixed. And it would be nice to have an operational dependency on your best estimate, but it has to be, of course, updated quite regularly. So I think what we need is a formula for merging from a historical observed values into near future scenarios, so that at any given time we can say, I want your best estimate for the next year of those 6 variables. And one way you don't at that point revisit all of the previous ones, you have a sort of second best, because you're going to do a gold standard every 6 years or whatever, for 4 years. But then it's updated, and the future might change every, in the next year when I take the latest one, you might have updated because you'll see we've emitted more methane or whatever, and you have to blend slightly differently to the scenarios. But it's then a time series I can pick up, and certainly the solar cycle will always be in sync on that kind of time scale. So is that the kind of thing you're thinking about with the sustained mode?
Yes, yeah. And actually what I didn't say is there is obviously a question about harmonisation if we're talking about scenarios. Like, does that have to be done every year? Perhaps it does. I don't know whether that horrifies people or not, but yeah, exactly. And this idea of splitting extensions from more, less frequent updates, I think, is important.
I'm assuming I can take the floor. Do you want to go first, Ben? Yeah, I think Robin's point is just a super helpful one. And it was actually a really helpful one in the task team. Like, as soon as we realized there's this distinction between extensions and updating, it was really easy to go around and ask people, what can you do? Half of us were doing updates, half of us were doing extensions. And then when you ask the teams, basically everyone was like, yep, we can actually do extensions as well. So we don't do extensions right now, but we definitely could. Now that we know that need exists, I think it's one we could definitely fill. And so I think even just knowing who's out there, who wants stuff and what they want, is super helpful. And the idea of doing a extension for 5 years, and then once every 5 years doing the gold standard update, like, sounds super sensible. And once you know it, it's not that hard to do.
So it strikes me that the IPCC has been strangely absent from this discussion so far. Like, and so the timescale of CMIP has always been historically defined by the IPCC. So I mean, I guess this is, and I don't have a strong position on this, but just to raise the issue, like, should we be still thinking that fundamentally we will have some sort of resonance with the IPCC cycle, and then the operational aspects should be then defined within that timeline? So, like, in this, and thinking about Colin's paper, for example, like, there's an opportunity to sort of provide data to all of the downstream activities in the latter half of this CMIP cycle, but it's still there's still an argument perhaps for just keeping the basic fundamental timescale linked to the IPCC cycle, but then sort of filling in a more concrete and predictable way what happens at various points in that cycle.
Yes. Okay. So what I would say is, I think if you asked a lot of people in WCRP, that they would say that CMIP isn't supposed to be necessarily delivering to IPCC. Of course, we know that isn't practically the case, but I don't think it needs to be driven by IPCC. In fact, I think you want to have things available, the more recent. But that's why maybe, I think a 7-year timeline would be too long for the updates, for example. So it could be 3.5, but 5 seems convenient since we know the global stock take is going to come every 5 years. So I don't know. I don't know the answer, Ben, but I'm not totally convinced that we have to stay coupled to IPCC. And as we've talked about with the fast track, the whole idea of that was partly to decouple things from IPCC, so everybody's efforts weren't forced by something which we're not even in control of their timelines, and it's not good for the science either on that sort of timeline necessarily.
Okay, Matt, a very quick comment, which just we better move on, otherwise we'll run out of time for the user session.
Sure, definitely. Just directly on this. So, I mean, I think it's also important to recognize that perhaps the IPCC should also be aligning its cycle with the global stocktake, right? And so if CMIP aligns its cycle with the global stocktake, then I think that also is helpful to invite the IPCC to assess the latest available science also in line with the global stocktake. So it shouldn't be the tail wagging the dog, basically. So I think it's a positive element, and that if CMIP wants to align with the global stocktake, then yeah, we don't have to worry about the IPCC. It should be the IPCC then also responding also to the ongoing political process as well, if it chooses to do so. Right. Thanks.
I'm just going to let Anna come in online.
Yeah, thanks. I can't help myself on this topic, but I'd be very careful in tying CMIP to the IPCC and how IPCC ties to the global stocktake. IPCC is struggling with this, and we see the situation without a timeline and a process that's really constricted because of the global stocktake. So I think IPCC really dug itself into a ditch by not agreeing to a product that was tailored to the global stocktake. And now everyone else, including all those in this room and the CMIP process, are having to deal with that. So we do have a knowledge of like the global stocktake process, which is very helpful. And I think that should be part of the discussion. And then I think how the community develops a sustained mode going forwards will inform IPCC's processes so that it is able to assess the most, progress in the science, so the time that takes, and then have something which is deliverable to the global stocktake. That's all.
Thanks very much, Anna. Anka, just very briefly before I'll hand over to you for the next
Well, no, I was
part.
going to argue against continuing to go on in round in circles, answering the questions until we've heard about the user needs that we were designing the session for. So I was trying to bring that to an end.
Okay, so over to you now.
In particular, I mean, it was nice that Robin intervened, not staged, by the way, in any way, because he represents a group of people who use and have interesting forcings from completely the outside perspective, completely outside the CMIP framework. So the next session was designed to address this, so to invite people more or less detached from CMIP to express how they use these forcings. They are using them already. They are already. But so far they have been just passengers and victims to the decisions that were made completely outside. So maybe this process would allow them to put the point of view forward. Before moving too much into the users or directly into the users, we have invited one of our colleagues who works at ECMWF for the Copernicus Atmospheric Monitoring Service, Johannes Fleming, who's going to tell us about CAMS, as we refer to the service, approach to creating things on what I think can be fairly described as an operational basis. So Johannes, your turn, please.
Yeah, thank you, Anka. I hope you can all hear me. Thank you for the opportunity to present here. My name is Johannes Fleming. I'm leading the team on aerosols and reactive gases in the research department of ECMWF. Just trying to get my slides up. I hope that's all okay.
Could you make them full screen? Can't really see.
They should be full screen now, Robin, I hope.
I think you might be sharing the wrong window. That's better.
Is it okay like this, or?
Yeah.
Okay, good. Though I'm talking about climate forcings in the Copernicus atmosphere monitoring today. You all know the Copernicus program, which is a space program of the EU. The main sort of purpose of the Copernicus service is to make use of the satellite data, because it has been recognized that just putting satellites in space is not enough. The services, of course, not only work with satellite data, but also with models and in situ data. Here are a list of the different services focusing on different topics. I think you're all familiar with the climate change service, and I will talk about the atmosphere monitoring service, which focuses on atmospheric composition. This is an overview of our production system that we use in the CLAMS service to provide our products. So for the global system, we use ECMWF's integrated forecasting system, which we have extended over the last 2 decades to be able to simulate also greenhouse gases, aerosols, reactive gases. And we assimilate atmospheric composition retrievals into the system to improve the realism. And of course, we also need input data for this, and for atmospheric composition, that's mainly different types of emissions, anthropogenic emissions, and also emissions from wildfires, for which we have our own SHIFA system, which produces these data sets based on FRP observations from MODIS. And also, as part of CAMS, we have a regional system consisting of 11 models, but I will not focus on this, of course, in this talk. So this is a list of an overview of CAMS operational products and CAMS science policy support products, which I wanted to introduce to you in a very broad sense. Though the most important one, I think, for your applications are our reanalyses of global atmospheric composition, focusing on aerosols, reactive gases, and greenhouse gases. But we also provide deposition fluxes and other derived quantities from the reanalysis. And together with the production of the reanalysis, which is continued always up to near real time. So we start the production, we cover a period of 20 years, and then when we reach a near real time, we do update the reanalysis only a few days sort of behind near real time to really have a very consistent data set up to the point in time where we are. But we also have an operational near real time forecasting system, and the difference of this system compared to the reanalysis that we updated on a, say, annual basis. So all the innovation, the new science and new modeling aspects go into the forecasting system, which can be changed all the time. And then when we start the next production of a new version of the reanalysis, we freeze the system and we use this then for the reanalysis. The emissions are also an operational product, and this comes clearly from the fact that we have those 2 operational systems. They need emissions, and hence also the provision of the emissions has to follow an operational procedure. And then we have a list of science and policy support products. There is one about reactive forcing, and I will sort of illuminate what we did for this in a second. CAMS has this commitment to service. That's probably one of the really defining properties that we have. And this means that we spend a lot of time on quality control and quality assurance. There are many aspects to it: evaluation, documentation, versioning, and well-defined process to transition research results into operations. I wouldn't say that we are sort of excellent on all these points yet, but we have the commitment to improve. We have the heritage of to be embedded in a sort of world leading NWP and climate center, but atmospheric composition has specific challenges. Just to name one, we have many more variables because we have hundreds of chemical species. We have emissions from many sectors. So in terms of managing data and huge, very variable data sets, that's really a challenge. All the data that we produce are freely available from the Atmospheric Climate Data Store. And we basically cover the period starting in 2003 when we had when the satellite data of atmospheric composition arrived. And also CAMS has a long-term funding commitment. So the products and the data sets we produce are not only available for a period of a project, but also for the long term. Just a couple of pictures, what we do with the reanalysis data sets. So as I already mentioned, we run the reanalysis in near real time, and that's why we are available in a very timely manner to produce plots like here in the middle, where we have the 2023 AOD anomaly compared to the reference period. So basically in January, we are already in a position to show these maps. And specifically for 2023, we see here the large positive anomaly of the aerosols because of the wildfires in Canada. Another application is the ozone hole monitoring. Again, that's a product that combines reanalysis data sets with our forecasting system. What we see in this graph is in red the extent of the Southern Hemisphere ozone hole, really right up to now, beginning of November in the red curve. And we see the envelope of the previous ozone hole extends in previous years going down to 1979. The two blue curves are the two previous years. So in 2024, we have sort of a really relatively average ozone hole. We are now preparing the next reanalysis of atmospheric composition, for which the production will start at the beginning of the next year. Just a few updates that we intend to do. We will increase the resolution. We will have fully stratospheric chemistry included. And we also are much better now in describing aerosols. We will assimilate new satellites, and I will come to this in a second. We have updated the emissions. And we are at the moment in this process that we try to define what we want to output to users. This is a list here of the potential products. But if you have any ideas of CAMS datasets that you would like to see from the CAMS reanalysis, which we currently don't provide, do let us know, and we can see whether it is possible to extend our product portfolio with these variables, for instance, specific aerosol optical diagnostics at certain wavelengths and so on. This is the overview of the different satellite retrievals that we will assimilate. In the different colors here are the data for ozone, NO2, carbon monoxide, and aerosol optical depths. The modeling version is, of course, frozen for an analysis, but the main challenge is really to recognize the different biases between the instruments and to make sure that they are all combined in this reanalysis in a consistent way, and that at the periods when new satellites occur, like in 2017, when Sentinel-5P arrived, that we don't have large jumps in the data set. So to make sure our reanalysis data set really is a very good description of the temporal variability and the trends in the last 20 years. This is an overview of the different emission data sets that we produce in CAMS. I just want to highlight here the fire emissions, the GFAS system, and also the global emissions from anthropogenic sources. And as I mentioned in the beginning, these are always updated up to near real time because we need them for our system. There are more dedicated specific data sets like shipping emissions or regional emissions. We also do have a growing interest in emissions that are based on observations. So we are developing CO2 emission verification system that will use satellite data to constrain the emission of CO2 and other greenhouse gases. So one specific data set I just wanted to mention in a little bit more detail is a data set which has been developed in two projects, CORSO and COCO2, which are all Horizon Europe projects dedicated to advancing the Copernicus Atmosphere Monitoring Service. And they came up with a very detailed data set of point sources for CO2, which we are also now implementing in the CAMS for the CAMS GHG forecast. I mentioned in the beginning that we had a project in CAMS led by University of Reading on radiative forcing products, specifically from the reanalysis. So the reanalysis is meant to be the best description of the current situation, and then in combination with pre-industrial simulations using the IFS, a large sort of portfolio of different radiative forcing products has been compiled and has been made available to users, focusing on carbon dioxide, methane, stratospheric, tropospheric ozone, aerosols, and so on. So these data can all be retrieved from the data store. The project is paused at the moment, but it will be revived when we finish the production of the next reanalysis. Just as a last slide, the CAMS operational forecasting system is embedded in the NWP IFS system from ECMWF. So we also have the opportunity not just to use climatologies as we do for the operational weather forecasting, but to use our prognostic aerosols directly. What is shown here, a case or the period of the summer 2021, where we had strong wildfires in Siberia. On the left-hand side, you see a graph of the mean AOD. The green curve represents the climatology. So these fire events are not represented. In red, you see the analysis, and in blue, you see a forecast over sort of 4 days. So already also in the forecast, these AOD increases were captured. And on the left-hand side, you find a plot where we see the improvements in the NWP scores for 2-meter temperatures because of using prognostic aerosols. So that's all I wanted to say. It's a little round show of what we do. And yeah, I found this meeting so far very stimulating, and maybe the conversation about the benefits and how to approach a sustained mode, operational mode, can be continued if this comes. Yeah, thank you.
Thank you very much, Johannes. If any questions come to your mind, please note them down. I propose we go through the couple more presentations we have, and then in the discussion moment, we bring these things up. Next, Tim Stockdale will tell us about other uses of information about forcings, which may or may not be fully satisfied by the CAMS outputs that Johannes described. Tim.
Okay, yes. But I need the microphone as well. Okay, Johannes gave a very nice detailed description of the CAMS system. I'm going to talk about reanalysis and initialized predictions, essentially seasonal predictions. I might make passing reference to decadal. And apologies slightly that I'm talking mostly from a sort of ECMWF perspective. But in terms of the data needs and the science needs, those are fairly common to other operational centers who are either doing reanalysis and also sort of seasonal prediction type activity. Each model has its own specific requirements, but as we go forward, as models become more sophisticated, the data needs will be similar. Just to give a brief outline of where we are now, we're running ERA 5. That is a reanalysis that covers the period back actually earlier than back to the 1940s, and also has a real-time system, ERA 5T, running a day or so behind real time. And that reanalysis system needs lots of inputs, as Robin mentioned, on the radiation scheme, solar forcing, greenhouse gases. You also need to specify aerosols, SST, sea ice, land surface, etc. ERA 5 is, as been mentioned, actually quite an old cycle. That system has existed for a long time. So it's a real mixed bag. Some things are CMIP7 data sets, others are just fixed climatologies. So the aerosol, for example, is just a fixed climatology. No, the aerosols, the sulfate aerosol has come from CMIP7, others are fixed. The seasonal forecasting system is updated typically every 5 years, sometimes takes a bit longer. There are reforecasts going back at the moment from the 1980s. Real-time forecasts run on the 1st of each month with initial conditions at 0Z. These are very operational. These really are operational in an NWP sense, such that in the initial conditions for our seasonal forecast, we are not allowed to use ERA 5 data. The ERA 5T, because that's not guaranteed available by 10 a.m. in the morning. So it's a very operational cycle. The forcing requirements in broad terms are similar to reanalysis, except with a forecast system, you have to provide the forcing data into the future as well. In our case, at the moment, up to 13 months. That will be 2 years in the next system. We don't need SST because we predict that into the future. And again, it's a mixture of things. It's basically the same vintage as ERA 5 in terms of the model. So some CMIP7, some fixed climatologies. For volcanic aerosol, we have normally a simplified damp persistence. So in terms of looking to the future and more general discussion of requirements, so reanalysis, we of course would like high quality data, and we would like data that is consistent over time. And that's desirable to facilitate the climate analysis. But it's worth pointing out a reanalysis system has a lot of data going in. So things like the temperature, there's an awful lot of data that constrains that reanalysis really quite strongly. So if you get errors in your forcings, your radiative forcings, for example, it's not fatal to your reanalysis. Having said that, there's a few caveats on that. ERA 6 uses a variational bias correction for most of the input data. So if there are discontinuities or drifts in the model bias characteristics, which might happen if you've got the time evolution of your forcing wrong, if your anchor observations are not working enough to anchor your analysis, you could potentially get into some trouble. And of course, there are some areas of the atmosphere where the data does not constrain things well, such as the upper stratosphere, and especially in the pre-satellite era, so your forcings will dominate things more. And I'll mention as well, reanalyses have their limits. Users have a terrible habit of using reanalysis as truth. And of course, people who work on producing the system know that's not too bad an assumption in some cases, but in other areas it really is not the case at all. So if we genuinely case in the past, if we go back to the 1940s, say, where there's very little upper air data in the stratosphere, there's maybe uncertainty in exactly what the ozone and other forcings were in the stratosphere in the 1940s, we're just uncertain, so that's okay. You know, we can't do better than the science. Another mention on reanalysis is traceability and credibility are also very important, and that's one of the reasons why it's very nice to be able to sort of follow community standards. CMIP is quite a nice cipher for that, and there are some areas where reanalysis might be able to do a lot of extra work on something. But there are other areas where we just pick up and say that is the community standard, that's the best data set we have, and just reference it. Just to illustrate in passing, so it's not just all text, this is ERA 5 temperature analysis in the tropics, going from 1,000 hectopascal up to 1 hectopascal. The top line is the actual temperature anomalies. And the bottom one are the mean increments, monthly mean increments. And this runs from 1940 on the left up to 2022 or something, 2021 on the right. So you see in the troposphere, you warm over time and you see some of the ENSO peaks. The stratosphere, you see perhaps broadly the opposite, some cooling over time, but you see that temperature evolution has lots of features in there some of which are not very credible. And your increments, if your model biases were the same, your mean increments are fighting your model biases, and you might like those to be constant with time. They're not constant with time. In the pre-satellite era, you don't have really much data in the stratosphere, certainly the upper stratosphere. And you also see there's some suspicious looking trends going on there as well. The tropical tropopause really gets a lot warmer as you go back in time until you get into the 1940s when you lose your radiosonde data, and then it cools down to what the model wants it to be. Those warmer tropical tropopause temperatures give a lot of extra humidity. Blue is more humidity. And it's not being driven by observations of humidity, it's being driven by the tropical tropopause temperatures. And I'll come back to that later because there's question marks about that. So that's reanalysis. For seasonal forecasting, the quality of the model and the forcing data is much more critical because we're forecasting 13 months in the future. If you've got the forcings wrong, your temperatures are going to evolve in the wrong way, and that is going to really hurt your forecast. We have, in a seasonal forecasting system, we have real-time forecasts, and they're calibrated against the reforecasts. model biases. So the sort of signals you're looking at on a seasonal timescale might be shifts in the PDF of 1 degree or maybe less, half a degree or something. And so the signal is small. The bias is not small compared to the signal. So you have to really worry about the bias correction. That's why you need the calibration against the reforecasts. And the really critical thing in a seasonal forecast system is that your model biases don't change with time, because you're going to estimate from the past and use them for your real forecast. And you might have a system that looks wonderful. You might do lots of scores on your past thing, and it all looks very consistent, very good forecast system. But if your real-time system comes along and you've made changes, or the data sets going into it are different and inconsistent, your real-time forecast might be bad. You might even be telling the users, look, we have our scores, we know the system is good, and you're giving them bad real-time forecasts. So it's a very serious problem. And so this consistency over time is completely crucial, and it's really challenging because most data sets, sort of observational type things, they're either produced as a sort of careful reanalysis for the past, but not available like today as a real-time thing, or they're sort of near real-time data sets that don't go very far back in the past. And having something that matches both of those, that's a big challenge. Another point I need to make in terms of seasonal prediction is that the climate change signal, which used to be sort of part of the background, has actually become a key part of the forecast. If we're predicting temperatures next summer in Europe, the climate change contribution to that is completely key. So we need to have all the processes that are driving those climate changes, we need to have them accurately represented in the model. And we need to know what is going on now, the latest things, are the cloud feedbacks, cloud aerosol things, are they changing in recent years? The very high temperatures we've seen last year, is that going to be sustained? What was driving that? That's all really important if you're trying to make a good seasonal forecast. Of course, it's not just temperature. We worry about other things, trends in the East Pacific, time variation of hurricanes, etc. And I could perhaps just comment, seasonal prediction is an excellent test bed for sort of climate change Earth system models. So forcing requirements, obviously long-lived greenhouse gases, as Robin was mentioning, ozone, I'm going to talk more about that in a minute, the solar forcing, tropospheric aerosols, volcanic aerosols. I'm not going to talk much about lake and vegetation and land use changes, but they're important, and we are addressing those for future systems. In terms of ozone, just to be specific, we have a linear ozone model that we use in these forecast systems. So Johannes mentioned in the full CAM system, they have a full chemistry model. We have a much more simplified linear system that we use in NWP and seasonal. It actually works remarkably well in most parts of the atmosphere. This figure on the upper right, the dark line is the CAMS reanalysis. The red is what you get with the ozone model as a multi-year run with just nudged meteorology. That's fine in recent times, but if we go back, particularly pre-93 and sort of pre-ozone hole, it's not going to work, because the coefficients for that scheme are empirically derived from the ozone analyses, from the previous CAMS reanalysis. So we need to retune those coefficients for past decades, and we're using the CMIP6 ozone data set to do that. So there is some dependence there on CMIP6 ozone, which there are question marks there about there are scientific uncertainties in ozone. That's a challenging thing, both at sort of recent trends and particularly the tropical tropopause region, and that actually is very key for reanalysis. These higher temperatures in the past that you see on the bottom plot there, if you run the model, we get the temperatures which are the blue and red lines. So in recent years, we're biased a little bit cold, but the much bigger problem is if you go back in time, well, our model says that the tropical tropopause temperatures, this is 100 hectopascal, should have been slowly warming over that period, whereas the radiosonde data that controls the reanalysis says it's been cooling, and you end up with a sort of 4 Kelvin bias if you go back to the 1940s. Now, those radius-on data are heavily corrected. There's a limited number of them. The instruments are not very good in those days. Do we trust the corrections? Do we trust the models? Do we know exactly what the ozone was doing? Those are big sort of science questions, uncertainty questions. But we have to worry about all of that with the sort of real-time system part of it. And longer term, we might also be able to make use of sort of full chemistry schemes. Solar forcing, in recent years, not in reanalysis, but we've been using CMIP6 TSI data. We're switching that to CMIP7. We've got all that ready, but I haven't picked up the 4.4 recalibration, so we will do that. But as sort of Robin mentioned, we also need future values, certainly for forecasts. So CMIP7, we now have a sort of revised data for the past. I've sort of made a little homemade forecast based on the NASA Marshall Sunspot forecast, which they've started doing, and some scaling assumptions. As things stand, that will just be a fixed data set. You'll see it doesn't have the monthly variability in it because the sunspot forecast is sort of smooth in time. This is something that a better treatment of that going forward might be possible and might be useful. Sorry, I skipped over tropospheric aerosols. This is where we've used the CAM system that Johannes mentioned. We've done a pseudo reanalysis from the 1950s where we force the meteorology. We don't have any assimilation of satellite data, but we run the full chemistry system with all of the winds and the emissions to give us time-varying aerosol. The emissions, we could not use the CAMS emissions because they only go back to 2003. So we've picked up so the latest version of SEDS, a specific value there. So a more recent one than was used in CMIP6, and then also CMIP6 fire emissions. So we've had to sort of do that, try and put that together. And this is again an area where we have some real-time data, we have some reforecast data, so some old data, but they're not really consistent, and there's a harmonization problem there. And yeah, that was just a one-off, and there's various ways one could imagine that being done better in the future, but again, we would need to find some resources to do that. Maybe in the next financial settlement for CAMS, we might advocate for some of this, and maybe other sources. Volcanic aerosols, previously we've done very crude representation of that. For ERA 6, C6, we have available the GLOSSAC 2.2 data, which gives us good vertical resolution. And also we're using EVAH from Thomas with specified eruptions. We're very dependent on the CMIP7 eruption data set prior to 1979 from Thomas. We can then use MS-Vol04. We plan at the moment that if there are any important eruptions in the future, we will just add those by hand. We've just got very simple sort of data sets we can do that. Can that become, part of a more organized international system for having an updated sort of near real-time data set of volcanic eruptions that is properly maintained? These two plots at the bottom, the upper one is the GLOSSAC 2.2 data. This is satellite data. You see Pinatubo is the biggest red signal. It's with height and time going along. You see all the small volcanoes on the right of the period. The bottom one is with the EVAH and driven by emissions. Something like Pinatubo looks okay. You see for the small volcanoes, there is some correspondence, but it's really not as good. So there's a lot of scientific issues around that as well. Equally, the satellite data in the 1980s is very ropey in these data sets. So, and I'm probably going to have to skip over discussion of optical properties, but we've recoded that in the IFS. We have particular requirements. We basically need to give a mass input. We do our own optics. We even needed to go and revisit the choice of the sulfuric acid refractive index that was being used. And choice of optical properties matters in terms of the impact you get on SST and so on. We also have some issues around particle size just after interruption. That's specific to the IFS. Lakes, vegetation, land use, ERA 6, these are basically fixed, but there's a project called Cerise, which is being funded, and this is helping develop time-evolving versions of these that will be used in something called ERA 6 land, which will run a little bit later than ERA 6, and it's a high-resolution land surface product. So there's a lot of work going on there, and that both depends on some things that were produced by the wider community, for example, LUH2, but also potentially produces data sets that might feed into the wider community. I wasn't sure whether SST is a forcing or not, but it is important. It's very important for reanalysis. And we discovered as part of preparing for ERA 6 that even in the 1980s, satellite era, the SST products were really a lot more diverse than we thought. And what we were originally planning to use, we decided we really couldn't use because the ENSO, the big El Nino event of 82, 83, looked very different to what we expected. So a lot of work has been done here in choosing which data sets we think are credible and which we don't trust as much. Just a few general thoughts on sustained mode extensions updates. So this, of course, has been said, extending things versus updating them. For sustained science applications, of course, we need both. But the extension is needed. It's really needed for applications where you've got a heavy investment and infrequent updates such as reanalyses, decadal prediction systems, seasonal forecast systems, and of course MIP-ERA experiments. So you want to, there's a strong use case for where you just take the same data and you just extend it forward in time. However, this is not as easy a thing as you might think. And in particular, if like the SEDS data, your emissions update, you get revisions of the last few years. Do you really want to use the latest data? How do you do that? And if you have a requirement also for systems that are running as real-time systems, how are you going to manage that? So there's two sort of paradigms here. So one is, the top one is the one I think that we have been talking about, which is where you do an extension and maybe once a year you release it and you extend the data by a year each time. Now, maybe that data set can go up to just last year or something with a 6-month delay. Maybe you want to have it with a longer delay if it's something like the SEDS emissions data. And that sort of annual release of updated data sets, I think, can work for decadal, for scenario updates. Particularly if you've got this lag built in there, it's perhaps less ideal for seasonal prediction and reanalysis because they'll always be using, they won't see these, they'll only be using this provisional input data set somehow. Another sort of paradigm is the bottom one, which is a little bit more how the operational systems like to work at the moment, thinking of how we do SST for reanalysis and how we might do some sort of emissions in the chemistry, where you have your fixed inputs, but then you really run your system where you have continual near real-time updates of your forcing things. So you don't have an annual release, but some data sets perhaps you can update almost in near real time. And you've got to identify which data streams that is possible for, and you have to worry then, because it's probably different to what you used for your past data, it's got to be very compatible. Say with SST is a classic example where you want to make sure that if you're using a daily operational real-time SST product, that's consistent with what you've done in the past. So for some data sets that might work, for others it won't. Some vague examples there, obviously greenhouse gas concentrations, anthropogenic emissions, they are sort of perhaps more an annual update thing, land use changes. Things like biomass burning emissions, You know, if you're having a big forest fire, you can't decide a year in advance where the fires are going to be. You want to have real-time data for that. Volcanic emissions data, again, if there's a big eruption, you want to put it into your system as soon as you know about it. Possibly solar data. If you're using sort of annual mean data, you can have it a year before, and you get, you know, you update it every year, and you'll get roughly the solar cycle, right? But if you want the sort of higher frequency fluctuations and things, and of course that is something that is observed essentially in real time. You know, the data for yesterday's TSI is not going to change. I mean, the calibration of it might change, but the observations are made. The data can be there. So there's some things that we could flow into near real-time systems. Are there some specific issues that we could identify that might benefit from better coordination? I might just mention that when you start talking about, you know, people doing operational forecasts, reanalysis, those give extra requirements, but they might also give extra resources. And then it can become a question of coordinating things that might already be being done and bring things together. I think things like fire emissions, possibly, as I mentioned, volcanic eruption data sets, there's a VolRes group, there's an email group, but it doesn't feel very sort of, to me, as sort of operationally or you know, can that be better organized? You know, what about the solar variation? Would it be useful to have a near real-time product of that with, we have access to the data, but we don't have access to updated forecasts of TSI. You know, how useful would that be? So with all of these things, and also for the ozone, consistent historical near real-time ozone, we have ozone analysis. CAMS does a whole lot of stuff. We have it in our NWP systems as well in reanalysis, but it's this consistency of reforecast going way back in time. CAMS, as Johannes mentioned, there's demand for going further back in time than 2003. But again, how do we put that together? So for these are things, it's a question of how strong are the needs, how feasible is it to do? Stop there.
Thank you, Tim. Tempted as you might be to ask questions, Paul, if you excuse me for a couple more minutes, no more than 12. I would like to invite the other 3 participants in a panel that we have asked to come along to bring their perspective. I think Tim has covered so much ground that we do want to return to what he's been bringing up. But we first have Leon Hermansson with us to tell us briefly about the requirements for initialized decadal predictions under the auspices of the WMO Lead Center for Annual to Decadal Prediction.
Yeah, thank you, Anke. Yeah, as you said, I'm kind of wearing 2 hats.
Muted himself, I think.
Leon, if you're still talking, we've stopped hearing you.
These are run on these are run with the same systems or similar systems. You know, fully fledged GCMs, like with all the forcings you might expect in a historical run.
Leon, I'm so sorry, we lost you in the room. Would you mind just starting again?
Yeah, of course, no problem. So today I'm representing the Decadal Climate Prediction Project, which is a MIP under CMIP, and also the WMO Lead Center for Annual to Decadal Climate Predictions, which are basically the forecasts on annual to decadal timescales. And both of these are linked, and the model systems are very similar or the same. And they're basically GCMs using historical forcings. And what we're hoping to get is annually updated historical forcings and kind of how they merge into these future scenarios. And they'll be used for decadal predictions and also to update our hindcasts. And I have to say, a lot of this is very similar to what Tim was talking about, so that was a great introduction. We go back to 1960 traditionally, So we need forcings from 1960 onwards. But also, increasingly, we also use large ensembles with single forcings to attribute forecast signals and understand what's happening in our forecasts. So the main thing we want is not to be in the position we are today, where when we run our forecasts in about a month's time, because we run them at the end of each year, we'll be using 10-year out-of-date scenarios, because we use basically the CMIP forcings. So CMIP6 historical runs, as you know, finished in 2014. So we're now 10 years away from when we last saw some real historical data, which we're going to be using for our forecasts for next year and for 10 years out. So it's not a great position to be in. So if we have something that's closer to where we are now, that'd be really helpful. Obviously, we're looking into the future. So what we need, the historical updates, these kind of extensions, as you've been calling them, is for them to be harmonized or merged into the future scenarios in a smooth way. But at least we have some kind of starting from a realistic place. And as I said, we run our forecast at the end of the year, so it'd be good to have something available, around now. And I think preliminary estimates are acceptable. It's better than nothing, as long as they're not very wrong. And then, happy for those to be updated later on, but we will obviously only be using preliminary estimates. So on the question of adding an extra year of forcings, the extensions, or updating the whole historical period, well, you have to remember that the hindcasts are used for bias corrections and to understand the system, as Tim pointed out, is a lot of integration, takes a lot of effort to make them. In the case of decadal predictions, you're talking several thousand years of integration, so it's not something we can do very often. If there are updates for the whole period, then there needs to be really clear metadata, so we can all agree in the community which version we're going to be using. And particularly DCPP are writing the protocol for CMIP7 at the moment, and if they could have like version numbers to specify in the protocol for what should be used to make the simulations intercomparable, that would be useful by summer 2025. Other questions we might be worried about is, can CMIP7 forcings be used for CMIP6 models? Because not everyone will be moving over to new models for CMIP7. And obviously the link between historical and future scenarios, that they give similar errors and biases, just like Tim just mentioned. So if this doesn't happen, how can we mitigate this? And the main thing is, things need to be as clear as possible, so we understand what's happening and what we're using, and that we're using the same thing. Thank you.
Thank you, Leon. Let's quickly move to Sebastian Milinski, who represents the Destination Earth program.
Anka, you should be seeing my screen now. My name is Sebastian Milinski. I work at ECMWF, and I'm coordinating the Destination Earth Climate Change Adaptation Digital Twin. So before I go into the relevance of forcings for Destination Earth, I want to give a very brief overview of what Destination Earth is about. So Destiny is an initiative by the European Commission to create a novel information system for a resilient society, to provide information both on climate change adaptation, but also on the impacts of extreme events. Destiny is implemented by ECMWF together with ESA and EUMETSAT, and we split the responsibilities as follows. So ECMWF is in charge of building the digital twins that are at the core of the system, as well as the digital twin engine, which is the software that allows us to run these simulations, handle the data flow and data provision. And for this, we are heavily relying on the EuroHPC systems to provide the computational resources for this. EUMETSAT is building the data lake, which is the central platform that stores all of the data produced by simulations, but also additional observational data sets for analysis and other data sets that might be relevant for users. And finally, ESA is building the core service platform, which is the outward-facing interface of Destination Earth, where users can interact with the data produced by the digital twins. Now, specifically, the climate change adaptation digital twin, which is using climate forcings. So this is an effort to produce kilometer-scale multi-scale climate projections in an operational framework. And the key features that I want to point out here is that these models are running at 5 to 10 kilometer resolution globally. We have 3 models, which are ICON, IFS FISM, and IFS NEMO that we're using. And with this resolution, we are able to provide global information with local granularity. And what this enables is that we can bring Earth system models and impact sector models within the same workflow, because the global models provide information at the scales that are needed to drive impact sector models. And what this allows us is to really shorten the time scale between providing global simulations to climate information produced by running impact sector models. With this system, we are able to do regular production, and this is what we are moving towards in the coming year. So to provide regular updates on simulations and new simulations, but also this system, this workflow that we set up allows us to run flexible on-demand simulations when needed. And finally, on the types of simulations that we're running, I don't want to go into detail on the actual models and simulations, but use this rather as an overview to show which forcings we're using. So the main focus of Destiny is on future climate change. And for this, we are using scenario forcing, so far SSP 370, from present day up to 2050. In the future, we'll also start using other scenarios. Then, of course, we need a period to evaluate the models. For this, we're relying, of course, on CMIP6 historical forcing. And our simulation protocol is a modified HIROSMIP protocol. Whereas HIROSMIP is starting historically in 1950, we are only starting in 1990 because these 5 kilometer simulations are so expensive that much longer historical simulations are not possible at the moment. And finally, we have control simulations, which are 1990 constant forcings. And then we have a special type of simulation, which are also called storylines. And in these simulations, we take present day greenhouse gases and so on, and nudge the large scale atmospheric flow to era 5. And then we take the same setup and move it into a warmer, +2-degree world, or into a colder pre-industrial or quasi-pre-industrial state. What this allows us to do is to ask how would the impacts of an observed extreme event unfold in warmer or colder climate. And this needs historical forcing that is up to date. So finally, I want to emphasize 2 points. One is that Destiny is obviously heavily relying on CMIP forcing. So Destination Earth is not producing its own forcings. It is using what the community is providing. And second, Destiny is not trying to replace the CMIP efforts. It needs CMIP as context to interpret the Destiny simulations. So Destination Earth is trying to provide infrastructure. It's not a research project. And finally, I want to come back to one of the points that Helene mentioned, where from the Destination Earth perspective, regular updates, extensions of historical forcing would be highly relevant. But updating the entire historical forcing, which would mean we would have to rerun historical simulations, is less relevant and less attractive to Destiny. And of course, the harmonization of historical and scenario forcing is highly relevant. Thank you.
Thank you, Sebastian. And last but not least, Jesus Fernandez is going to speak to us on behalf of Codex.
Hello. Can you see this?
Just before you start, we would like to extend the current session to a quarter to the hour, so by 15 minutes from the original program, because we would like to hear your feedback. I'm taking note of all the people who put their hands up and the order in which they've gone. Sorry, Seikla.
Just to comment that in session 3, we have additional discussion time for user requirements booked in, so there will be more time in plenary.
If we can have it in plenary, though, that would be.
It's plenary breakouts and then report back. We've got an hour booked in for more user requirements discussion.
But we want the immediate feedback. Paul has been waiting too long. I don't want to.
Yeah, absolutely.
Okay, but let's hear from Jesus first.
Thank you. So this is Jesus Fernandez from IFCA in Spain, and I will be talking about the climate forcing needs from Cordex, just to set a little bit the background on Cordex for everyone. Cordex is an initiative from WCRP, which currently sits behind the RIFS, WCRP core project, the Regional Information for Society, and it stands for the Coordinated Regional Climate Downscaling Experiment. So the idea is to downscale, that is to increase the resolution, to translate the global model output to local scales, to regional to local scales. And for this, we use different tools. We use regional climate models mainly, also convection permitting regional climate models, which is essentially the same, but at increased resolution, reaching kilometer scale. And we also have other techniques such as empirical and statistical downscaling, and more recently, machine learning RCM emulators. So Cordex is essentially a regional community-driven initiative. So the communities work under the same umbrella, but they are more or less independent from each other in the development of their analysis and so on. And there are two main kind of activities for the regional communities. The main one is the continental scale downscaling. So there are different domains which are in the figure here, not full continents, but quite large domains, and the downscaling is done at the whole domain extent. There is science at this scale, but there is more recently, and with a shorter time scale, also these flagship pilot studies, which are focused science projects, focused on particular aspects. I will be talking about a couple of them in a second. Last but not least, there is Cordex Core, which is an initiative which is across the regional communities and trying to provide a homogeneous data set across different domains for the whole world. So giving you a bit of background of the history of Cordex is totally aligned with the CMIP initiative, because for the downscaling, we need the global model output as boundaries for our models. So here I put what used to be called just Cordex is what now we can call Cordex CMIP5, because we were nesting into CMIP5 model output. And now we are currently under what we call the Cordex CMIP6, because we are downscaling models from the latest generation from CMIP. For reference, I put here these symbols, which mean when do we have an experimental protocol for a given Cordex round, let's say, and this is the symbol for when we have an archiving specifications for the output. This more or less signals the place or the time when people is already producing simulations. So there is quite a long time that we need in these different communities to really setting up their networks and getting funding to really do the simulations. One thing that changed recently from Cordex CMIP5 to Cordex CMIP6 and beyond is the resolution. The standard resolution for Cordex CMIP5 was around 50 kilometers, and this is now deprecated. In Cordex CMIP6, the minimum resolution is 25 kilometers, and most domains are running with 12.5. And there are even several flagship pilot studies which are working at convection permitting scales from 2 to 4 kilometer grid spacings. So just to give you an idea, this is in some sense similar what Destiny is mentioning also about the kilometer scale global simulations, and this is also the result here. The main difference is here the ensemble size. We are really sampling a lot of uncertainties here. And this is the total number of simulations, scenario simulations expected for the different domains. These are current plans. Yesterday, let's say, this plot, and here we can see the progress of the simulation from Cortex CMIP6. Apparently, from this plot, we are progressing quite well. The black part is when simulations which are already complete, and the green part is going on. So there is activity in most domains. The problem is that even if in a short time we should be able to complete the simulations that are planned, the main problem right now is to have a homogeneous, this Cortex score, which means that we should have a minimum amount of simulations for all domains, and this is the problem, because this is mostly driven by the problems with the funding. There, for instance, in Australia, there is a funded program to get these simulations done. In Europe, there are several projects already going, but the problem is to get funding to really do simulations, to ask money in Europe, for instance, to do a simulation in South America, to really have a homogeneous data set to work with globally. So with these time scales that I have been talking about, Cortex seems less concerned with the forcings, the sustained forcings with the extensions, the yearly extensions or the updates with 3 years. This is really, with the timescales I've been talking about, not really a concern for us, and we would be more concerned with the support that this data set that we decide at the planning stage is really still in place and usable when we are really doing the simulations. This is in general for the current way of thinking of Cortex, but if Cortex moves towards other tools which are currently bleeding edge, such as the emulators or the FPSs, are also quite interested in the latest results, because these FPSs do the actual focused science that then fits back to the continental scales. So focusing on the climate forcings that we are using in Cortex, the main forcing for us in principle is the lateral boundary conditions from the driving GCM. So this means that we need actual model output to really run the downscaling, not just the climate forcings. And in fact, is a pending subject to consistently incorporate the climate forcings in Cortex. For instance, our latest protocol, Cortex CMIP6, is discouraging, but is still allowing to use a static land use for the scenario simulations, or to use a basic aerosol treatment. So the vision for the next cycle of Cortex is really to use a fully consistent forcing with the GCMs, as we have been seeing along these days in the workshop. Regarding these two climate forcings, there are specific flagship pilot studies dedicated to analyze the effect of these forcings on the simulations. This is just very briefly results from the FPS aerosol. There was a large problem in the Cortex CMIP5 simulations over Europe, because some of the models did not use variable aerosols in their simulations. And this is from a very recent study showing how, when we consider evolving simulations, we have a consistent signal with a proper warming in Central Europe, which is gone when we are maintaining the aerosols constant. That's why the specific protocol for Europe regarding aerosols is mandatory now for Cortex CMIP6 to use evolving aerosols in our RCS. This is one example. Another one is from the land surface, the land use and land cover data sets. We developed over Europe, again, a product which is called LandMate, which is based on the ESA CCI land cover product, which is at 300 meters. This was translated into 16 plant functional types that are used by the RCMs over Europe, with 2 different resolutions which are adapted to the use in EuroCortex. One is about 10 kilometers and another is about 2 kilometers, which provide us nice land cover data sets to be used at convection permitting time scales. Moreover, in the FPS Lucas, they also mix this static land surface product with the land use harmonized dataset version 2, and they use the land use transitions to create time series for this evolving land use for the past, for the historical, and for the scenario simulations. This is done for Europe. This work would be extended and has been extended for North America. For the moment, at this 10 meter resolution. But when we go to higher resolution, to these convection permitting simulations, we would need higher resolution data on land use transitions, including this the scenarios. So this is the last slide, just a summary of what has been said. Not surprisingly, what Cordex needs is essentially higher resolution in the spatialization of the forcings that have been extracted from the SSP scenarios, and in particular, we can say about 10 kilometers for the continental domains and about 1 kilometer for convection permitting simulations. This includes aerosols, and importantly also something that has been mentioned, I think yesterday, about the evolution of the urban scenarios. There is currently in the land use scenarios a single category for urban, but our urbanized models handle different categories within the urban areas. Some of them are, for instance, these local climate zones you might know about. These are subtypes within the urban environments, which might change also with the development of the cities, depending on the growth in the population and so on. Maybe different subtypes of urban cover will evolve in the future, and this would be nice to have at very high resolution as well from the SSPs. So I will stop here. Thank you.
Thank you very much. My suggestion would be to focus now briefly on clarification questions for the speakers that have introduced the requirements, and return to the discussion as to the likely chances of success of these requirements, the judgment on the compromises we've heard about in a session that Claire mentioned we will have afterwards. So unless there's any strong objections, Paul, please.
I'd just like to thank everyone for the presentations, because it's given me a perspective that I didn't have anywhere near as clearly. I know that Gavin has made statements about, how deep the contributions of CMIP actually flow, but I did not realise that Eastern WF was heavily dependent upon what we've been doing as a kind of a somewhat of a smell of an oily rag kind of science project. That to me is kind of stunning, actually. And a question that I'd be asking is actually two questions. When did this dependence happen and why?
A long time ago.
But like in all honesty, like when and why? Because the thing is that in CMIP5, for example, we didn't coordinate the forcing data sets, any which like in CMIP6, we put them in a SGF basically and try to coordinate them reactively rather than proactively. And in CMIP7, we're doing a better job proactively rather than reactively. But the fact that you guys have picked up these things and started running with them, like how far back does it go?
It goes back a long way. And I think, I almost think possibly even before my time, which is a very long time. So once you realize that your CO2 needs to change, then you need to get time varying CO2. And of course, the CMIP data sets were the natural ones to go for. And then as the model has developed slowly more towards an Earth system model, more processes are involved. It's a similar thing. These things have been very peripheral to ECNWF, which focuses on the NWP. So it's not had the sort of resources that we have for the main model development. And it's just, we need to pick up, okay, greenhouse gases, we need, what about volcanic aerosol? What are we going to do for that? So the go-to place has been to go and see what the CMIP community has been doing. So that's sort of historically how it's evolved. And often it's been implemented in a sort of simplified cut down way, even, because it's just been done in a little bit of somebody's time.
So the reason I asked the question is that in one of the WCRP documents that I can't find at the moment, I think Kath came up with a number, which was, this is how much has been invested in the CMIP, enterprise since dawn of time. If you add ECNWF and a whole bunch of other operational centres, that number gets a couple of zeros on the end. And it means that, like, why are we doing this on the smell of an oily rag if we've got hundreds of millions or potentially billions of dollars that are being spent at the end of the pipe to use all this stuff? And, how beneficial would it be to every forcing data set provider to get a nice letter and a medal from Eastern WF to say thank you very much, and please keep doing it. And by the way, we've got a new funding call that's opening, next January. Please feel free to bid for it because, you're doing a great job. Thanks very much. I mean, at the moment, we've got letters from WCRP that's saying, thank you very much, modelling groups. Thank you very much, ESGF contributors, etc. Like, there's a lot of goodwill here again, but how can we quantify the goodwill and quantify the impact, which is what Helene's been kind of dropping in the chat too. If you guys are dependent on it, please tell everyone, upstream that you are, because it's core that we hear this so that we keep, trying to figure out ways of doing it better.
Now, Carlo has an immediate response. And then well, I thought you did, yeah.
There is something, I don't know whether it's the response you have in mind, but there is something, well, on the letter and the badge of honor, we can do it now. So it's that's straightforward. But, picking up from the discussion online, and again, I think my brain is hurting having all this channel of communication in parallel, but picking up from the discussion online, I think that there is more than can be done. So I think the idea of recognizing the fact that there is a community that is using the forcing now, and all the talks, I agree with you, were quite eloquent. So the Codex community, the seasonal, the reanalysis, the CAMs, and so on. I mean, there are Destination Earth. There are a number of users that are using this information now, and this for me calls for, makes the call for operationalization, and then we can discuss what that does it mean, but, to the continuous stream, much more compelling. So that's the element. And so the two things go together. On the one hand, supporting the community to give the recognition that they need, but on the other, making even stronger the case for the continuous forcing. And in the specific on how to assess the value to the community. So there are some examples. We started working on an assessment of the value, economic value of the reanalysis. It's incomplete. Many of us have been quite critical about the methodology, also because we are all physical scientists, and many of these methodologies rely on social science skills. So maybe we don't even understand how they work. But these are the standard in the community, and actually they bear weight when you deal with funded. So maybe picking up from some of these points and using the same approach, and we were discussing online with Helene for the CMIP and Codex community could be useful. And then there are some also applications that also emerge in the chat. For instance, there is the European Investment Bank we are working with, and now because of legislation drives, the European Investment Bank or any financial institution in Europe, in fact, have to disclose their climate risk. So they become user of CMIP and projection. So that's an even possibly another couple of zeros, if not 3 zeros to that number that you're talking about. And this needs to be documented as well.
Sorry to butt into your conversation, but this has gone in a completely wrong direction. I wasn't expecting to bring the other conversation in now, later this afternoon. I think it deserves talking about. And whilst I appreciate Paul's concern that, people have not recognized vociferously enough, I would have hoped that you'd also pick up from Tim's presentation the number of compromises and shortcuts and patches that he had to put in place. So as much as he's depended on the stuff that comes from CMIP, the stuff he's done with it, you might not want to endorse in full. So I would say bear that in mind.
So, Anka, I can't help but butt in on that one, because this is one of the things. I mean, Zeb made the comment that there are orders of magnitude that have many more zeros now if we actually have this use case down the end. And so let's do a better job and figure out how to actually do a better job.
Let's return to it later, yes. But I wonder if Ben has just given up because he was bored, or because, or whoever put the flag there, either Ben or Chris, I don't know who had the flag up earlier. Okay, so it's gone. You had a thing up, I've written it down. Your thing. Okay, fine. Claire wanted to say something, and maybe Helene. I don't know in what order, Helene, if it's an immediate response.
I had a possibly slightly uncertainty-related question for Tim, rather than anything broad overview. And maybe it's relevant for CAMs as well. How much of, so you use a lot of the CMIP forcing data sets. How much of that is because you need something that spans the satellite and the pre-satellite era? And there are not very many data sets that do that in a consistent fashion. Is that part of the equation? And I'm thinking of Carlo's comments about variability characteristics of the data sets from yesterday. Is that something that we should pay attention to, that community that needs to span?
It is part of it, definitely for reanalysis, which wants to go back in time. And on the seasonal stuff, the real-time forecast we calibrate at the moment from sort of 1993 onwards. A lot of the CAMS data sets only go back to 2003. So, but then we like to also produce seasonal forecasts going back into the pre-satellite era as well to give a wider perspective, particularly of winter variability. Yes, so that those issues absolutely come up, and those question marks. I know some of the data sets, CMIP data sets, they're so different when you go back in time. Land use as well is another thing that they're very what's the word, the characteristics change, and that is a challenge.
Okay, Vaishali, you are a new flag. I suggest you wrap it up and then we head for lunch and return later with full force on the same subject if you wish.
Sure, and this was more of a clarification, technical clarification question. Tim, I was intrigued by the way you prescribe ozone, and actually I couldn't understand how do you use the CMIP6 when you do have a linear ozone model as well?
So the linear ozone model has coefficients, and the first key coefficient is the mean net rate of the chemical production or destruction. And then there's also a mean concentration that you relax back to, and then there are time scales and temperature sensitivities and other linearizations of the chemistry. It's slightly tricky because if we take the CMIP6 ozone data sets, they've been produced by models, but those ozone concentrations are changing. So, okay, how good are the models? How consistent are the data sets? How consistent has been put together? That's actually quite big uncertainties there. But there's also a sort of methodological one that if the stratospheric circulation changes, the ozone concentration will change. If the temperatures change, the ozone concentration will change. Our scheme already includes those things. It will get those corrections correctly. So we need to isolate the part of the ozone change that is due just to the chemistry changing. So we have to estimate that and try. We're not going to be able to do a very clean job. That's going to be a bit of a dirty patch. And it's what I'm actually working on at the moment. We only need that data pre-93. The production of reanalysis will start later than that. So we've got a little bit more time to sort that out. But yeah, it's a slightly messy business.
Okay, thank you very much. Tim will return this afternoon, I hope. So think up more questions if you have any. I hope maybe the other participants in this panel can return for a while this afternoon if we return to this conversation. But for now, I thank you very much for preparing your introductions and for nicely identifying the needs that weren't already covered. And I leave you to enjoy your lunch. We return at
I would suggest we come back at 20 to 2, so 13:40. For the in-person people, can we meet in the docks for at 1:30, 13:30 for a photo, please?
Okay, and we return to plenary or to breakout groups? You take over and tell people where to come back.
We have plenary 2 first, and then the breakout group is in plenary 3. Yeah. Everyone online, could you turn on your camera quickly? And we'll do an online screen grab photo, please. And yeah, it'll appear publicly, so if you don't want to show your face, don't, essentially.
Can I ask as well, if people want to chat during the break online, that people stay on their cameras and chat on the break if they have time?
Great. Right, a few more cameras on.
Do we need to leave the spy behind so we can listen into what you are going to be talking about?
Okay, another couple of seconds and then we'll take the photo. Okay, go, Riley. You need to look. Oh, sorry. Okay. Okay. Thanks, everyone. We'll turn off the sound in the room so you guys online can just keep chatting while we're having lunch. Thanks very much.